All right, welcome to Homebrewed Physics. On the last test, you had a problem that involved the damping of a oscillator, a simple harmonic oscillator, and I wanted to investigate that a little bit here with a little demo. What you have here is a spring, and notice that the spring here is a little wider at the top, a little narrower on the bottom, and if you look through, you can see that the coils are together at the bottom. They're not spread out, whereas at the top they are. Okay, this spring is to be done in this fashion, and when you hang it that way, you can see that the spring is fully engaged throughout. It's the tapering of the coil diameter that allows the entire spring to be engaged in the same way. As you pull down, then each coil is opening or closing the same amount throughout the entire length of the spring, as opposed to in this direction. As you pull down, as you can see, the spacing at the top is bigger than the spacing at the bottom. Okay, so this is a much more expensive spring than you normally get. So what we have here is a spring. I will put a mass on this spring. The spring will bounce up and down. At the very bottom here is a motion detector. It's a range finder. It measures the distance for every certain amount of time. It measures the distance, and then it will plot on the screen using Vernier, which you have access to. Vernier graphical analysis. It can then plot both the position and the velocity as a function of time. Okay, so let me get this set up and I'll come back to you. All right, we're back. What I have done is I have set up the weight, the mass, so it goes more or less straight up and down above the motion detector at the bottom there. I have zeroed it. I stopped the mass moving up and down and zeroed it. And when I run it, you can then see that it is symmetric up and down about 0. Okay, just to show you what it's doing, I can run it again. Oops. And rescale it. Okay, and you can see that it is, plus or minus 4 is the amplitude, and the velocity is nice and constant. And you notice that the amplitude here is fairly constant. Now, if you ran this for 3 or 4 or 5 minutes, the amplitude will start to decay away. But for the most part, you can see that it is fairly constant here. The period, of course, is from the maximum to the maximum, from the maximum to the maximum, according to either of those two graphs. And this is the setup. This is the setup that I have going here. It's just the straight string, or the straight spring, with the mass going up and down. And from that, we can calculate the spring constant of that spring. And as you saw on the graph, it is simple harmonic motion. That is a sine wave. Whether you want to call it a sine wave or a cosine wave doesn't make any difference. It's just the starting point. But you can see that the velocity and the position are 90 degrees out of phase. When the position is at maximum, the velocity is at 0. And when the position is at 0, the velocity is a maximum. That is the hallmark of simple harmonic motion. What I will do at this point is to add something to this spring. Notice that the period here, I'm going to count the very, very rough measure of the period. This is 20 seconds long, and I'm just going to count the number of peaks here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 peaks in 20 seconds, if I counted that properly. That'll give you a rough idea of the period. The period is the time between peak and peak. So again here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 peaks in 20 seconds. So it's a little bit So they both are just the same there, obviously. What I will do is add something to this spring. You can see that the spring, it's stretching. According to the graph, it's stretching 10 centimeters as it goes up and down. It does decay away. I'm going to simply add I'm going to add a rubber band to it and see how that changes things. And we will be back. Okay, we are back, and as you can see, I have added a rubber band over half of the spring. There's a rubber band right here. Yeah, you can see it there. I have attached the rubber band from the bottom to here, which is about halfway along the spring. Effectively, now when the spring stretches, not only are the coils increasing in size, but the rubber band is stretching. So effectively, the spring constant of this thing has changed. Okay, I have re-zeroed it again. Let me get it started moving up and down. It's bouncing a little bit too much. That should be all right. Let's go over to the screen and see what this looks like when it's running. And you can see right away that the amplitude is dying much more quickly. I could have extended that rubber band all the way to the top and it would decay even more quickly. What you have is, well, first of all, the spring constant has changed, right? And let's count the period. Remember, this period it's simple harmonic motion, so the period is going to be related to the spring constant. Let's get rid of that stupid pop-up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 peaks. But without the rubber band, it was 17, I think. So the period has changed a little bit. On the test, it says that the period remained constant. Depending on the rubber band that I used, the period would be more changed less or more, depending on the spring constant of the rubber band itself. But what you can see here, it is decaying away. You still have that same, Jesus, all these pop-ups. Oops, where'd it go? Here we come back. You still have that underlying simple harmonic motion shape, the sinusoidal wave. In addition to that, you have an envelope. Okay, the envelope. If you can see my finger here, okay, the finger goes down. This is an exponential, so you get this sort of exponential decay above and below. Okay, exponential in true sense of exponential, as in E. All right, you're going to have the sine wave, and it's going to be multiplied by some function of E, so it'll be E to the minus T over tau or something. Where that tau is the decay constant of it. It's going to damp. We call that damping. It's going to damp the amplitude. Okay. The question that I want you guys to ponder is to figure out why it damps. Okay. Remember that the amplitude is related to the energy. So the energy is going away. Where is that energy going? Okay, and why is it changing here when I have the rubber, so much more drastically when I have the rubber band versus the spring? Okay, they're both stretching. Okay, I mean, so you see both are there. The spring is stretching, and you can see, by the way, the Christmas stuff there. The spring is stretching and the rubber band is stretching. So why should the two of them stretching, as opposed to just the spring stretching, change the shape, the decay of that simple harmonic motion? Without the rubber band, it still decays. Only you'd have to sit here and run it for 5 minutes before you could see something. Okay, just adding that simple rubber band makes it visible within 20 seconds. Okay, just as a reminder, physics is fun.